Assalamualaikum to Dr. Fazilita. We are from group WHIHB Engineering and we are going to present about the belt conveyor system based on our design and analysis we have done. This is our group member. The first one is BREDLEY DEXTER, which is our group leader. The second one is Muhammad IZZAT NAUFAL, which is me. The third one is HAFIZUDDIN, and the fourth one is Muhammad Haris, and the last one is WILLDRON Wilson. Okay, I'm going to talk about the introduction, project scope, and objective. In modern industrial automation, all is about efficiency. Our goal was to design a system that can transport products, specifically a 3 kilogram trace over a total distance of 10 meters with maximum reliability and zero human intervention. To ensure the reliability, a steel support is placed beneath the belt to prevent sagging under load. For the system architecture, this design consists of three main units. The first one is an electrical motor to provide the primary energy source. This energy is distributed through a four-gear arrangement, which to manage speed and torque. Finally, the drive drum, which act as the critical interface, converting that rotary energy into the linear motion that move the belt. Because this is a mechanical design project, our technical scope is strictly focused on three significant engineering components. We analyzed the drive shaft for bending and torsion. We also selected appropriate rolling bearings to handle the rotational loads, and we designed the threaded fastener, which is necessary to secure the entire assembly to the conveyor frame. Our goal was to develop a system that is not only efficient but also safe and meets specific load parameters. Specifically, what we aim for are to maintain a constant belt speed of 0.7 meter per second and achieve a mechanical efficiency of 90%. And we also determine the exact rotational speed and power necessary to transport our load at a constant velocity. Moving on to the next slide, which is the design specification and assumption. To ensure our calculation were grounded in real-world performance, we established fixed parameters and assumptions. The motor operates at 870 rpm. The drum diameter is set at 0.25 meters, which has been given. We selected the material AISI 1040 steel for the shaft material to provide the best balance between the strength and cost effectiveness. We also assume there is a friction, which is the coefficient of friction is 0.35 between the belt and steel support plate. Finally, we calculate the based on the steady state operation with 20 trays spaced 0.5 meter apart. Next slide is the system power and force analysis. Now looking at the kinematics to achieve our target of belt speed, which is 0.7 meter per second using a 0.25 drum. We use the rotational speed formula. As you can see here, the required drum speed is 53.48 rpm. When we compare this to our motor speed of 870 rpm, it reveals that our gear arrangement must provide a total reduction ratio of approximately 16.27 to 1 to maintain the correct belt velocity. Then we analyze the dynamics of the system with 20 trays totaling a mass of 60 kg. We calculated the force required to overcome the friction. Using the friction coefficient, which is the 0.35, we determine that the motor must overcome a frictional force of 206 Newton. This translates to a required torque at the drive drum of 25.75 Newton meters. These values are critical because they dictate the diameter of the shaft we select and the types of the bearing required to support the rotational load.
Moving on towards section 4.0, component design and selection. My name is HAFIZUDDin bin YAHYA, BK23110057. I will be presenting the shaft design analysis for the drive drum BH. Our primary objective is to determine a safe diameter to prevent failure from combined bending and torsional fatigue. For our material, we selected AISI 1040 cold drawn steel. We chose this because it provides a high yield strength of 490 megapascal, which is essential for resisting permanent deformation and fatigue, better than standard hot rolled alternatives. To determine the actual forces acting on our drive shaft, we started with the 206 Newton force required to move the 90 kg payload. However, we cannot design the shaft using the pulling force alone. Following design 11.1, we replaced the belt system with a statically equivalent load. We applied a 3:1 tension ratio, which is a standard engineering assumption for flat belts. We use this specific ratio because in a real-world system, the belt must be under tension on both the tight and the slack sides to ensure the drive drum has enough friction to transmit power without slipping. This established a total radial load of 618 Newton. As you can see in the free body diagram, this load acts at the center of the drum, creating reaction forces of 309 Newton at the bearing and a maximum bending moment of 115.875. This data serves as the foundation for our fatigue analysis. For the calculations, we utilize the ASME design equation, incorporating the Soderberg fatigue criterion. We use a design safety factor of 2.0 and accounted for the stress concentrations from the gear hatch keyway with a factor of 2.1. By plugging in our torque of 25.75 nanometer and our bending moment, the math resulted in a theoretical minimum diameter of 29.96 millimeter. Finally, we have selected a 40 millimeter nominal diameter for the drive shaft. While 30 millimeter is mathematically safe, the 40 millimeter choice is a practical engineering decision for three main reasons. First is compatibility. It matches the UCP 308 pillow block bearing selected for the system. Second is the standardizations. It allows for a standard 12 by 8 mm keyway for gear hatch. And lastly is deflection control. The increased diameter provides the rigidity needed to prevent shaft sagging, ensuring belt tracks correctly and doesn't wear unevenly.
Hello, my name is WILLDRON and I will be presenting the threaded fastener design. So our main objective here was to ensure the UCP 208 bearing housing are securely mounted to the conveyor frame and can withstand continuous operational vibration. To achieve this, we selected an M12 by 1.75 metric hex bolt. We specified an ISO class 8.8 material, which is a quenched and tempered medium carbon steel. This will provide a solid proof strength of 580 megapascal. While the bearing housing can actually fit a 14 millimeter bolt, we stepped down to an M12 to allow some clearance for alignment adjustment. To compensate for the clearance, our design requires standard hardened flat washer to ensure the clamping load is distributed evenly across the mounting slot. Moving on to the load analysis, we took the 309 Newton radial load from the drum and distributed it across the two bolts on the housing, resulting in a maximum external force of 154.5 Newton per bolt. For a non-permanent rigid joint, we targeted a preload of 75% of the bolt-proof load, which comes out to roughly 36.6 kN. To achieve this specific clamping force, we analyzed the bolt tensile stress area, which is 84.3 square millimeter, and applied torque coefficient of 0.2 for standard unlubricated zinc plate steel. This calculation led us to our final assembly recommendation, a tightening torque of exactly 88 Newton meter. Finally, we verified the safety of this joint against yielding and shear failure. Under maximum preload condition, our yielding safety factor sits at a very comfortable 1.33, which perfectly aligns with standard machine design practices. When looking at shear, our safety factor is a massive 208. To give context to that number, the actual shear stress acting on the bolt cross-section is only 1.83 megapascal, while the material shear yield strength is over 380 megapascal. Because the forces generated by the 3 kg trays are so minimal compared to the capacity of an industrial M12 bolt, our design is exceptionally safe. The integrity of this joint will rely entirely on the friction grip generated by that 88 Newton meter installation torque. That concludes the fastener design validation. Thank you.
My name is Muhammad Haris bin Muhammad IQBAL, and in this slide, I will be presenting about rolling element bearing selection. For this section, we focus on selecting a suitable rolling element bearing for the drive shaft at drum BH. The bearing must safely support the radial load generated from belt tension while ensuring long service life and reliable operation. From our shaft analysis, the radial load acting on each bearing is 309 newtons. The drum rotates at approximately 53.48 rpm, and the required service life is 20,000 operating hours. The shaft diameter selected earlier is 40 millimeters, so the bearing must be compatible with that dimension. To evaluate the bearing life properly, we use the ISO 281 basic rating life equation, also known as L10 life, which corresponds to 90% reliability. This ensures that at least 90% of identical bearings will achieve the calculated life under the given load conditions. Okay, in this slide, we calculate the required dynamic load rating of the bearing. First, we convert the required operating life from hours into million revolutions using the equation L10 equals 60 times N times T divided by 10 to the power of 6. Substituting the values, we obtain a required life of 64.18 million revolutions. Next, we apply the basic rating life equation for ball bearings, where L10 equals C divided by P to the power of 3. Rearranging the equation to solve for C, we calculate the required dynamic load rating. After substitution, the required dynamic load rating is approximately 1.24 kilonewtons. This value represents the minimum load capacity the selected bearing must have to satisfy the design life requirement. Okay, for this final slide, final bearing selection and the justification. Based on the calculated requirement of 1.24 kilonewtons, we selected a 6208 deep groove ball bearing integrated in a UCP 208 pillow block housing. This bearing has a bore diameter of 40 millimeters, which perfectly matches our shaft design. More importantly, its typical dynamic load rating is approximately 31 kilonewtons. Since 31 kilonewtons is significantly greater than the required 1.24 kilonewtons, the bearing provides a very large safety margin. This ensures long-term durability, reduced risk of premature failure, and stable operation under continuous conveyor use. Additionally, the pillow block housing simplifies installation and maintenance, making it a practical and cost-effective choice for the conveyor system. Therefore, we conclude that the selected bearing fully satisfies the mechanical design requirements. That's all for me.
Hello, my name is BREDLEY DEXTER Anthony, and now I'm going to present the part engineering drawings and justification. So here are the system layout and the component assembly. So the first picture is the 3D assembly view of the conveyor belt. Next is the isometric, the side, the front, and the top view of the gear placement. And next is the exploded view of gear system, the shaft, the fastener, and the block bearing. Moving on to our engineering justification, the selection of material for this conveyor system was driven by three critical requirements: fatigue resistance, vibration damping, and tensile strength. Our goal was to ensure a long operational life while maintaining high precision. For the drive shaft, we selected AISI 140 cold-drawn steel with a yield strength of 490 megapascal. It provides the necessary endurance against the constant bending and torsion the shaft faces during operation. For the spear gear trend, we upgraded to AISI 4340 normalized steel. This deep hardening alloy is incredibly tough, allowing the gears to handle high torque and contact stresses without pitting or bending over thousands of cycles. To keep the system running smoothly, the UCP 208 bearing housing are made of gray cast iron. Its unique graphite flake structure acts as a natural dampener, absorbing vibrations from the motor and belt to ensure quiet operation. To secure these components, we are using ISO class 8.8 steel fastener. These are quenched and tempered to reach 800 megapascal tensile strength, ensuring they maintain their preload clamping force even under heavy machine vibration. The slider bed support plate used 3mm ASTM 836 mild steel. It's a cost-effective choice that provides a rigidity needed to support 3 kg trays without sagging. Finally, the conveyor belt itself is a composite of industrial rubber and nylon ply. We specifically chose a rubber surface with a high friction coefficient of over 0.3 to prevent tray slippage and ensure efficient power transfer at our 0.7 meters per second operational speed. This combination of high-strength alloy and damping materials creates a durable, efficient system ready for industrial use. And that's all for my part. Thank you.
This is the last part of our presentation. To conclude, let's look at the final outcome and our recommendation for the system. Our design successfully meets all the technical requirements. We have validated that the gear reduction ratio of 16.27 to 1, which allows the system to maintain the target belt speed of 0.7 meter per second. From a safety perspective, by using AISI 1040 steel for the drive shaft and ISO class 8.8 volts, we have ensured the system is resistant to fatigue and vibration. Furthermore, the selection of UCP 208 pillow blocks, it guarantees a reliable service life of 20,000 hours, making this a robust solution for industrial transport. For the recommendation, to maintain this performance, we recommend 3 simple steps. For the first one, we recommend to establish a monthly lubrication schedule for the bearing and gear train. The second one, perform a regular top checks on the mounting bolts to ensure the preload remains intact. And finally, utilize the self-aligning features of the pillar blocks for periodic belt tracking adjustment to prevent uneven wear. With these measures, the conveyor is ready for long-term efficient operation. Okay, that's all from our group, and thank you.